Todd May. Welcome.
Thank you, Dennis. Hey, thank you. I was told to stay on the blue carpet. Hey, so I'm really excited to be up here. This is my first time up here to this event, and it's kind of a payback to Ken Kramer, who's on the board here, and he's been coming to a lot of our events over the years, and he said, you really got to get up here. Guys like John Grunsfeld and Bill Gerstenmaier and Jim Green have done the talk, and it turns out I've worked for most of those guys, and a couple of them have worked for me, so it's great to be part of this. The other thing I really like about this is raise your hand if you know where you're going to be on August 21st, 2017. Yeah, I'm going to be in Calvert City, Kentucky, so I get it. So anyway, thank you for having me here today. I'm going to talk a little bit about exploration and tie some things together, I hope, and as well as give you an update on the Space Launch System. Marshall Space Flight Center has a long history in exploration, both of humans and the type that you like. We were heavily involved in the early development of the Hubble Space Telescope and the Chandra Telescope, and we still operate with the SAO and Harvard, the Hubble Telescope today, as well as the development of the Saturn V and all of the propulsion elements for the Space Shuttle, and now the development of the Space Launch System. So I grew up in a small town on the coast. No, I didn't grow up on the ship, but I would go down to the coastline a lot when I was a kid and look out at the horizon, that thin line that separated the ocean from the sky, and always wondered what was beyond it. And some things kind of clicked for me later on in my career. If you go back, what I loved about the advertisements you were seeing is they showed the astronomy, and then they showed the JFK speech where we say we choose to go to the moon. But if you really look at that speech, there's a lot more in there. One of the things he says is that space is the new ocean, and we intend to sail it. And that's when I understood that exploration and discovery is really universal. Whether you're an astronomer and you're exploring with your eyes, or you're a scientist and you're exploring with your mind, or we send robots in the planetary world to other bodies, celestial bodies, and we explore robotically, or we explore with human feet like we have on the moon. But also through history, exploration is also kind of universal. If you've ever seen old maps, they have usually up in the corner that little dragon with the humps coming out of the water, kind of like Loch Ness. And it would say in Latin, in the really old ones, Huc sunt dracones, which is here be dragons. And if you watch The Right Stuff, the intro there, they say, kind of this dramatic voice, he says, there was a demon, they said, that lived in the sky. He lived behind a barrier. They call it the sound barrier. And if you ever went beyond it, you would die. And I think that's kind of universal, right? Whether it's the ocean or whether it's the sky or whether it's space, there's also a little bit of danger when we send humans out into that unknown. And so, of course, these are the Nina, Pinta, and Santa Maria. My grandmother actually gave me these models when I was a kid of these ships. And so I always understood that idea that space really is the new ocean. And like probably many of you and that father and that son in the advertisement, my dad actually used to take me out to see lunar eclipses near the Gulf Shores where I grew up as a kid. So enough about that. I'll talk a little bit about Mars first. Of course, I came from the National Space Symposium this week where they had all the center directors lined up, and the final question by David Livingston, who was our moderator, was, what are you doing to get us to Mars? And of course, Bob Cabana at Kennedy says, well, we're building the launch complex that's going to launch the rockets. And I said, we're going to launch the rockets. And it gets to Mike Watkins, who's the director of JPL, and he kind of said, well, we're already on Mars. So yes, we have definitely gotten to Mars robotically. At one point in my career, I actually had the chance to sit console when we landed Phoenix. I sat right behind the project manager, Barry Goldstein. And it was a very visceral moment to actually vicariously explorer. And when the first pictures started coming up, I was in the room with the scientists, and I felt like an explorer. But you know, Mars is hard. And some of you may have seen this graphic before. What it is working from the outside. If you see the various colors there, those are the colors of the lines are the various countries that have attempted to get there. And at the end of those lines heading towards the center is either a green check or a red X. And the red X, unfortunately, means mission failure. And as you move in, the circles there, you go from a flyby to an orbiter to a lander to a rover. And what you'll find if you look at it closely is that the United States has had a pretty good record. Many other countries have not, and more than 50% of the missions to Mars have failed. It's a tough prospect. The moon was hard, but Mars is even harder. And so I'm going to talk a little more about that as we go forward. The other thing I'll point out on this slide is this quote here, "Reach new heights and reveal the unknown for the benefit of all humankind." That's actually NASA's mission statement. And there's about 17,000 people that work for the agency all over the country, and we get up every day, and this is what we get to do. This is our mission. And it's really fun to be part of the agency, and particularly fun to be part of the agency at this particular time. Because at this particular time, we are establishing commercial ability to launch humans into deep space. We are building the most powerful rocket we have ever built. The James Webb Space Telescope is going to launch next year. We are celebrating more than 15 years of permanent human presence in space, and we are working on going deeper than we've ever been. So, as I said, Mars is hard, and I think Bill Gerstenmaier has spoken here before, and he's probably talked to you a bit about this. But if you really think about where we are today from a human perspective, we're in what's called low Earth orbit, and we're pretty much Earth dependent. If something fails on orbit, we build another unit and we send it up. And we can have astronauts down in hours if we needed to, if there were an emergency. If you want to get out to Mars, you're talking about a multi-year mission. And when you do that, you're going to be Earth independent. And you really have to rethink how you do reliability, maintainability, and logistics. If something goes wrong on the way, you're not going to send another unit up. You're on your own. And that really has caused us to think differently about what we're going to do when we go. For example, you may want the ability to make 3D parts of just about anything you need and have on a stick all the drawings of the entire spacecraft. You may want to deconstruct the racks so that you can get to just about any part you need to. You may want to make everything as common as possible so you can borrow from one area and put it over in another area. Those are the kind of things you've got to think differently about. You've also got to think about things like performance, especially when it comes to things that we're real interested in at Marshall, like regenerative life support systems. Whether you have regenerative water or oxygen, those are two things that we humans, it's one of the reasons that the rockets have to be really large. We're pretty needy. And today on the International Space Station, our performance is about 40% to 70% recyclable. We want to get that up into the 70 to 90% range. And our reliability is on the order of 6 months, 6.5 months. We need to get that up to about 2.5 years. And so we really need the next generation of life support systems as well. So Mr. Gerstenmaier recently, last week, actually rolled out a plan to the NASA Advisory Council of what we would do in what we call the proving zone. That's out in cislunar space. You're days away there, but you can still have a supply chain if things go wrong. And his plan is basically a successive series of missions where we are able to stay longer and longer out there in deep space. And there'll be more coming out on that in the coming weeks and months, but that is what we have presented to the NASA Advisory Council in terms of how we would move forward. So I talked about the fact that we humans are pretty needy, and if you're going to go out to Mars, you're going to need a big rocket. I would tell you about 4 or 5 years ago, a lot of folks were thinking, why don't we just use a whole lot of small rockets? And I think we kind of consistently said, no, things are going to, they get larger, especially when people get involved. And if you really look at just about industry, any industry from time immemorial, whether it's rail or whether it's planes or whether it's cargo ships, the trend they've gotten bigger, not smaller. Particularly if you have a complex architecture, the reliability actually goes up in your mission if you have a smaller number of things in bigger chunks. So this is your current fleet, if you will, of the new ocean-going vehicles. The ones on the far left are actually operational today, and you probably recognize a number of them, or maybe have seen a launch of these. This is in the largest capability we have today is about 24 metric tons. As you move over into the middle, these are actually in development today, and you see a couple of new entrants in this world as well. One really popular one these days is the Falcon 9 Heavy, and then you see a series of SLS vehicles beginning with the Block 1. The Block 1 capability is 70 metric tons to initial mass to low Earth orbit. And then once you add the upper stage, that takes you to 118, and once you add the advanced boosters, 130 metric tons. Our plan is to get to the Block 1B, the 118 metric tons by the second launch, and we're currently developing the Block 1. And then out to the far right, you see some notional vehicles that have been presented that go even bigger than that into the future. So a little bit about the Space Launch System. This is the most powerful rocket ever built, and it is out of design and in build today, and I'll talk a little more about it. It can lift a payload up to 130 metric tons once you add the upper stage and the boosters. Because of that, I mentioned that it reduces the risk of missions, particularly long missions, and it also reduces the timeline. It also can be game-changing in terms of science and technology, and I'll show you some illustrations of that here in a second. And it moves us forward into an innovation economy. The rocket today is being built around the country, over 1,100 contractors in 43 states. 800 of those are small businesses. So if you look at kind of the payload capability here on the far left there, you see kind of the largest 5-meter fairing we have today, and there's a person down there, a little white shadow shows you the size of what a human is there. But when you start with the first construction of the 8.4 meter fairing there in the second. That's a conceptual view of what like a Europa mission would look like. And the really neat thing about the Europa mission for us, we see a big advantage is that if you take any existing vehicle today and try to launch it, you can't go direct. You've got to spiral out. It takes about 7 years to get there. With an SLS, you can get there in 2.5 years. And I actually worked the New Frontiers program and the New Horizons launch with Alan Stern, and it launched over 10 years ago. And we got together for the flyby 9 years later. And let me tell you, you get older. We both had gray hair this time when we saw each other. And a number of our colleagues who started out with us in that mission are no longer with us. And it really can make the difference in a mission when you're just getting started, or whether you're going to be there to see the science on the back end. And then you see kind of in the middle there, that's the initial configuration with the Orion, but you can actually put another payload up under that once you add the upper stage, and that can be anywhere from 6 to 10 metric tons. And so you could have a secondary payload even when you're launching an Orion. And as you move to the right, something you may be interested in, really large telescopes, and I'll zoom in on that capability here in a second. And then to the far right, once you put the 10-meter fairing on, now you're in the Mars class, and you can actually take those really large things you need to be able to get to Mars itself. And this is just kind of an illustration of what we're talking about, and this was done working with Dr. John Grunsfeld and some of our friends over at Goddard. But you can see on the far left of this picture, that's the Hubble mirror today. And then the second one there is the James Webb telescope. And I know we're all really excited about that. But as you move over to the right, you can see an architecture that's enabled by the SLS that takes it even another level. And you guys can do the calculations in terms of what kind of science that could enable for astronomy. With respect to mission capture, I mentioned a little bit about the ability to open up the outer planets, but this is kind of illustrative. We use a term called C3, which is essentially the energy it takes to get somewhere. And if you see that orange solid section down in the bottom, that's all current. That scopes all current launch vehicles today. So that far left grouping of launch vehicles that I showed you on the previous chart. And then as you move up the screen there, the green is the initial 70 metric ton capability, the blue is the Block 1B, and then once you add the advanced boosters, the red is all the way up to the Block 2 capability. And then as you move across the right to the chart, you can see the various celestial bodies you're trying to get to there. And so you see, for example, out to Europa for the Block 1B, you can get up into the 17 metric tons. So we currently are working on the Clipper mission, which is an orbiter, but if you want to land, it actually takes a pretty heavy payload. I think they're currently estimating the lander to be 16.9 metric tons, and you can see that that Block 2 is about the only thing that can enable that size lander. So I'll just tell you a little bit about SLS. It's actually, as I said, being manufactured as we speak today. The engines for the first 4 flights are actually already down at Stennis and built. These are flight engines that flew on the shuttle. We have a new state-of-the-art flight controller, and that first flight unit has actually been put on the test stand, and we fired it here a few weeks ago. And so those things are doing great. The ICPS, or the Interim Cryogenic Propulsion Stage, which is our interim upper stage, is illustrated here in the bottom right. The flight unit is actually at Kennedy already. We've done all our qualification testing. We actually stretched the tank, and then we built the flight unit, and it was delivered a couple weeks ago. The boosters themselves have completed qualification, and we're in the midst of pouring all the flight segments. I believe we had a gentleman here from ATK. He probably talked a little bit about that a little while ago. And then the core stage, which is our large new development, that's a 27.5-foot stage. It's down at, it's designed by Boeing in Huntsville. It's being, the big pieces are all being built in Michoud outside of New Orleans. All your major pieces of that core stage now have completed the welding process, and we're in the process of outfitting those things. We put the TPS on the tanks, and we put all the plumbing and the electronics in those sections. And so the qualification stages, where we actually build up a version of these things to structurally qualify them, will be shipped up to Huntsville. All those test stands now are complete, including one test stand for the hydrogen tank that's over 21 stories tall. It's almost the height of a football field. The barge that we use to push the core stage around, we actually took the old shuttle external tank barge, we cut it in half and stretched it 65 feet, and it's now longer than a football field. And that's just for the core stage. You see it represented by the Pegasus barge here. The machine on the left is the vertical assembly center. That is basically our most interesting piece of manufacturing equipment. The old external tank on the space shuttle took about 30 different stations to be able to make the external tank, and a lot of that welding was done in the horizontal. We now do all of that work with only 5 major stations, and we use what's called self-reacting friction stir welding. This machine right here is over 200 feet tall, and it's accurate within 10,000ths of an inch, 2 10,000ths of an inch. And the way we do it is we put the pieces into the machine, and then we have 2 weld heads that just go around with an operator sitting in a chair. We lift it up, and then we put another one in and do the same thing. And then when we're done, we pull the whole thing out, and we have an entire tank. It won't fit vertically in the building, so we actually have to build the 2 halves horizontally and then put them together. And then once we put them together, we take it out the back and put it on that Pegasus barge. The first flight when we build, we'll go to Stennis Space Center, and we'll take that entire core stage and put it up on top of the B-2 stand. And when we do that, it will be, I believe, the 2nd tallest structure in the state of Mississippi. I think if it were in New York, we wouldn't stand a chance. Let's see, I'll also mention that the avionics are all those avionics boxes now are through qualification, and we have a facility in Huntsville where we call it the SIL. We take all of those pieces and we put them around in a mechanical structure that simulates the full diameter of the core stage, and we put the full length wiring to make sure we have all the right line loss and things like that. And so we've done that with development units, we've done those with qualification units, and now we're populating with flight units, and we're on our last version of software now. We're actually testing with the flight version that also has a subunit that is to do the test at Stennis. And so we're moving closer to launch. We've been working really hard. All these pieces are being put together, and we're looking forward to shipping the rest of this down to Kennedy and kind of turning it over to them, and then they stack it up and get it ready to launch. So a couple other things to consider here is that, as I said, Mars is really hard in a couple of different ways. From a technological perspective, there are a lot of different technologies that we're going to continue to push as we move into the future. One of the problems that we haven't completely solved is in-space transportation to Mars. And so there's a lot of different trade studies out there in terms of what we might do. The current thinking is we're going to work on solar electric propulsion and kind of scale that up. But one of my personal favorites is nuclear thermal propulsion, and so I'm pretty bullish on that. We've been working on that at Marshall Space Flight Center for a long time now, and we think it's very efficient and reliable, and it's really good for pushing the crew out to Mars. On the left, one of the other things we have to work on is making things less expensive and really changing the industry thinking in terms of how you make things. What you're looking at there is a 3D printed turbo pump that we have actually built and tested. We built it in a very short period of time. We put it on the test stand. We spun that turbo at 86,000 RPM. That's actually 3 times faster than the Space Shuttle main engines. And we put 20,000 pounds of thrust out the back end. A lot of folks are hearing about additive manufacturing, and you know, pretty much anybody can purchase one for their desktop, but there's not a lot of folks out there that are doing it with high nickel alloys and doing it with the kind of tolerances it takes for turbo machinery and things like that. So we develop these things, we push it out there, we have different vendors around the country that build the parts, and that kind of moves the industry forward. And then we work on things like the standards. What's it going to take to be able to certify these things to actually be used in rocket engines that push humans around? We also are interested in composites. We believe that as you move into the future, composite tanking and things like that are going to actually make the rocket lighter because of a thing that, if you're a fan of this kind of stuff, my favorite astronaut talk is Don Pettit talking about the tyranny of the rocket equation. It's really hard to get anything up into space because of that stupid equation. And if the Earth was a little bit heavier, we wouldn't even be able to get off the planet. And so we end up having to be very efficient and push the limits of the materials and the processes and things like that. Composites are better than metals, but we have to push those into the future. This is actually one of 3 machines in the United States that can do very large laydown of plies. You can actually customize your thickness as you go across the parts and do it out of autoclave and do large structures in very complex shapes. And so we believe this is also going to be kind of industry changing. We also think that this is where the commercial airplane industry is going in the future as well. So we don't just do rockets at Marshall. As I said, we've got a long history in science, and so we recently competed in a small Explorer class mission. Marty Weisskopf, who's actually the project scientist on Chandra, was part of this team. And it was announced over the Christmas break that we won the IXPE mission with our partners Ball out in Colorado. This will study some of the most energetic phenomenon in the universe. And again, you guys know more about this than I do, but like supermassive black holes and magnetars and things like that using X-ray polarimetry. There's a technology in here that we are kind of best in class at using. It's incident grazing, optics, and things like that. So we're really excited about this. We're just getting started. We've assembled the team, and in a couple years we're going to get this one up and flying and start really getting some really interesting science out of that as well. So I know we're at a community college here. I don't know how many students are in the room, but I will tell you from a NASA perspective, we've got a lot of folks that will be retiring in the next few years, and we're looking for you. We believe that there's a large untapped resource out there in this country, especially in minorities and females. They don't tend to choose engineering and STEM as much as the more traditional folks out there, and so we are looking to hire, and so you see here that we're really interested in getting you into NASA. We think that folks like me are getting old, and I'm going to be beer in hand, toes in sand here pretty soon, and we need that next generation to come in. So I think with that, I'll tell you that you can't spell Marshall without Mars. And it's funny, it took me a few years to even notice that. So with that, I think I'll just take any questions you might have. But thank you for having me today.
My first experience with astro imaging was in the 80s with a silver film, and it was quite painstaking. My parents, they bought the Celestron 8, and they let me doing my hobby. And I was the happiest teenager of the world. I was dreaming in front of the brochures with all the telescopes.
First major discovery was in 2006 on February 24, Universal Time, 25 local time. It is during that time when I took an image of Jupiter, and I discovered that its white spot oval BA has turned red. This spot is now known as a red spot junior. I had some people saying that, why the hell are you wasting your time in the middle of the night just imaging planets? And this is where amateurs fill the gap. And this is how we contribute basically to the development of the science of astronomy.
Celestron has always been about imaging. When I got that Celestron 8 back in 1975, one of the things that attracted me to it was it appeared to be built from the ground up to adapt directly to photography. The modern electronic imaging makes it so much easier for anybody to get into this and achieve good results quickly. People saying, oh, I just started imaging in 2008, and they're producing observatory quality work. Or I've only been in it for 10 years or whatever. And I'm thinking, my God, I'd already been doing it for almost 4 decades by the time they even started. So that's really been a joy to me, that the passion that I've been able to enjoy for 5 decades, now everybody can get in and do top-notch work right off the bat.
You know, the rock case was one of the first cases I used a microscope in, and it became a huge case. And sometimes it's not the actual evidence that's there that leads you down a different road. Sometimes it's what's not there. So it's just things like that that may seem unimportant at the time, but become very important when you're testifying in trial. And I wouldn't be able to confidently testify to things like that without the use of the technology and use of the microscope.
They've been great for our curriculum because these students come in with very little knowledge of using microscopes, and trying to teach them on a standard microscope is very difficult because you can't see what they're seeing. I think with students today, they've grown up with technology, they expect technology, and then they get in the classroom and there's no technology. So having that technology there, I think, makes it feel more real to them, and I think they're just everyone's fascinated by microscopic things anyways.
With these microscopes and the nice big large size of the panel, everybody can see what they're supposed to be looking at. I do love that everybody can be involved, and we have 6 of them, and so easily the entire class can be looking at different parts of the same insect or the same slide all at the same time. So sharing has just been really a plus, and they love it. They're so involved in what they're doing because the microscope is fun to use.
I think introducing birding and bird watching to other people is very important to the recreational activity of birding. The spotting scope is great. The Celestron Regal spotting scope it's really versatile, and one of my favorite things to do with that is digiscoping, and so that it's great. You don't have to carry your bulky camera around. You can just I carry my iPhone with me, and I do a lot of my photography with that, and with the Celestron scope it's just a clear picture.
Very competitive by nature, and when I got into imaging, I wanted to be good at it, obviously, and just like with golf and anything else really. But it's funny, just like with golf, there's all different types of people that do it, and trying to fit in, my hobby with being a golfer and a dad and a husband, I mean, it's tough. So I've learned to process very, very quickly. I've become very efficient at it, and where some guys would spend, a week on one picture, sometimes I'm cranking one out and, over coffee in the morning.
Can one filter street lights?
Yes, street lights have a few emission lines, primarily sodium and mercury, that can be selectively filtered.
What can you see on Mars?
On Mars, with this telescope, you'll be able to see the polar ice caps. You will also see some dark Maria features on the surface of Mars.
Celestron has been instrumental in our support of teachers in their quest to birdwatch and identify birds and engage students in birdwatching. They've donated many pairs of binoculars to the Cornell Lab of Ornithology's Bird Sleuth K-12 program, and we've been able to pass along these binoculars to teachers. Kids love tools that they can use to do science. If you put a pair of binoculars around their neck, they become scientists.